Hey, what's up, guys? John here again. So this time, let's take a look at another LeetCode problem here. Number 1368. Minimum cost to make at least one valid path in a grid. Hard problem. I like it. Very interesting problem. So basically, you're given like a m times n two-dimensional grid, and on each positions, there's a value from 1 to 4. It represents the direction of the arrow, basically. So 1 means right, 2 means left, 3 means down, 4 means up. And right, so basically you're given like this, for example, you're given like this like 4 by 4 2D arrays. And on each of the element represents the direction of the arrows. And you can only move the to this direction. And then okay, so what is ask you? It asks you, okay, one more thing is that you can change at any, you can once you're at any cell here, right? You can modify this arrow direction only once, only one time only, right? Basically, you can modify this one from pointing to the right to pointing to down, right? And the cost of doing that is one. Right. So, and then it asks you to find the minimum cost to make the grid, basically the minimum change you need to make so that you can travel from the top left corner to the bottom right corner. If the basically if you're traveling along with the arrows, there's no cost. Only when you want to travel to a different direction, uh, comparing to this arrow, then you need to add your cost by one. And they ask you to find the the minimum cost to travel that to down here, right? Very interesting problem. Okay, so let's take a look at some examples here. So here we can change three arrows to make us travel to this target point. And the example two here is here. If you follow this uh, examples, right? If you follow this path from if you follow the path, okay, from here, oops, sorry, from here to here, and then here and here and here, right? So in this case, you don't need to make any change of any arrows. All you need to do is just follow the direction of the arrows defined, and then you can travel from start to the end point, right? So at the beginning, when I saw this problem, I was thinking, okay, since we have this kind of definition here, can I use DP to solve this problem, right? So I was like, okay, can I try to define a 2D DP, basically DP DP INJ, right? So DP INJ represents at the current position, what's the minimum cost I need to make so that I can arrive at this current state, right? Uh, that's like a normal uh, uh, attempt, right? Basically, no, normal attempt. And then while I was trying to write the DP state conversion function here, I realized that since we have since this arrow can be changed to any direction, right? Basically, both up, down, left, and right, which means that, for example, if we're at DPI and J here, let's say if we're at this position here, right? Not only it can be reached from the previously row and column, right? But it can also be reached from the future row and column, right? Let's say we can also reach this dp and j from dp uh, I plus 1, right? And j, or the ij plus 1, which are the states we hadn't been calculated yet, right? And you guys may already know that one of the preconditions of using DP to solve a problem is that all the sub problems to get to the current state has to be calculated beforehand already, right? When we are at this I and j, basically we cannot depend on any future or slash uncalculated states to calculate to get our current state, right? This is like interdependent, right? Interdependent to each other, which cannot be solved by the DP problem. Cannot be solved by the DP technique here. So then if we cannot solve it by DP, then the only choice we have here is the graph, right? Basically, we have to do a, and then I was like, since it asks us to find the minimum cost to make to find the final place, right? Final target position. I need to use the breadth first search, right? But then I got stuck again because I was like, with breadth first search, how can I build this graph, right? So because we have the graph here, let's say we have I was like from the 0, 0, I can freely travel to any of the following positions by no cost, right? Then I was like, can I try to build like a graph such that from the current positions, uh, if it can be traveled to any of the positions without any cost, then I will add that edges to this current position, right? And then I was like, if that's the case, how about the ones that the positions that we cannot be traveled from here, right? How can we add those edges, right, to the graph, right? Because to be able to travel from the start to the end point, right, we need to have like a complete graph of each of the element, right? If we're only considering the places we can travel from here, then how about those ones we cannot travel, right? And so so that because of that, the normal mm, native breadth first search graph will not be helpful to solve this problem. And so what we need to consider is a graph with a weight on each edge. Yeah, this is also kind of new to me because I never built like a graph with weight before. But now I saw this problem, and one of the takeaway for me is the next time when I see this cost, right? Cost to move from one place to another, I should have thought about a graph with weight on each edges, right? Okay, so with that being said, what we need to do here is that at each of the position I and j here, right? I and j, we try all four directions, right? Basically, we'll be adding four edges to the current I and j, right? But the only difference here is that those four edges have either zero or one cost on top of the edge, right? As you can probably you guys already realize that if the edges is following the same direction as this arrow here, right? then the weight on that edge will be 0. For all the other edges, right, the weight will be 1, right? So this will be 0. This will be this will be 1. Then this will also be 1. Go up, it's not a valid edge, right? So and now after traversing all the element here, we have built like a graph with edges with wedges with a weight on each edge, right? And then now the problem is converted to to calculate the minimum path from start to the end point, right? Because it asks us to get the minimum cost, which is the weight on each edge, right? So we just need to calculate the minimum weight, total weight on the edges from 0, 0 to this endpoint M and N, right? And that for that we need to use the Dijkstra algorithm to solve this minimum path, right? The minimum or distance or minimum weight, whatever you want to call it, from start to end point. Okay, so with that being said, let's try to code this problem, and I will be explaining a little bit more about the Dijkstra problem while we're coding it. Okay, so first thing first, and let's build the graph, right? So M equals to the grade, right? N equals to the grade uh, 0, right? And then we also need to build the directions, right? So what's the direction here? We have to have a 4 directions here, right? 4 directions here is the directions. And since in the future we'll be using these values, right, for each of the direction. For to make it easier to compare uh, the current arrow direction with the direction itself, right? I'm instead of using a simple array here, I'm using a a, di a dictionary. But you know what? Let's try to use this simple like list here to represent 4 directions. Let's see if we can if this will work with that. Then we don't have to make it like a dictionary. So first is the right, right? So the right is going to right is 0, 1, right? And then going left is going left is 0, -1, right? Same for the down and right. So for going down is the is 1, 1, 0, right? And then for going up is -1, 0. All right. So now let's try to okay, so graph, right? So we're gonna have a graph with a default dictionary. It's a list, right? Since each uh, uh, position could have up to 4 edges. That's why we're using a list to store all the edges for the current position. So then just simple nested for loop here for j in range n, right? So now we need to have 4 directions here, right? For now the another place is the 4 directions in directions, right? So for each directions, we need to find we basically we have to compare with the we need to have a weight here, right? Basically, I'm gonna have a weight or cost. Yeah, let's do a cost. Yeah, instead of weight, maybe the cost is it's more appropriate for this problem. But you know what? Actually, I'm going to use a weight because weight is a more generic to for all of the graph problems. I'm going to use a weight here. So at the beginning it's 0 and right, and then not 0. So it has to be either 1 or 0, right? So for 1 or 0, it depends on the grade of the value itself, right? It depends on the grade value of I and j, right? Basically, if this thing is 1, then this weight for this direction will be uh in this direction, the weight on these edges will be if the same as this direction, then we will be having like a weight equals 0. Otherwise, it's going to be 1, right? So you see, we have to somehow link this 1, 2, 3, 4 with all these four directions, right? How we can link them? Of course, we can have like a if else, right? We can have like four if else here to check uh if it's 1, then we know it's 0, 0, 1, right? If it's 2, blah blah blah, right? So for me, I instead of using the this direction here, instead of using a list here, I'm using a dictionary here to add uh, one more layer on top of these directions. And so basically the key of the directions will be this 1, 2, 3, 3, 4, right? And the value will be this thing will be the offset of the x and y, right? So for that, we have to change these directions from a list to a dictionary, right? 3, 4, right? So now if when we when we like loop through this direction dictionary here, now the D here becomes to either become to 1, 2, 3, and 4, right? And then we can simply use the this direction to help us determine what uh, what's the weight for this edge, right? Basically, if this if this thing is the same as if this the key is the same as the current direction here, right? Then we know the cost will be 0, right? Else 1, right? So that's the current weight of the edge. And then okay, and then we basically we will be creating our graph here, right? So the key will be the current position, right? And the value will be the new one, right? So the new one will be actually, you know what? Let's create new I uh, equals I plus directions, right? Dot D because we need to get the offset from the dictionary here. So the offset will be the first, it's 0, right? And new J is to J plus same thing, right? Directions D dot 1, right? And then let's do a simple boundary check here, right? So as usual, right? And I am and same for the new y coordinates, right? New j n. We only add basically we're only adding the valid edges, right? And the value for the edge for each edge will be new I, new j, and the weight, right? Okay, so now once we finish the first nested for loop, we'll be having like a graph with weight on each edge, right? So now, okay, so build graph with weight on each edge, right? So now we need to implement the Dijkstra uh, algorithm to help us get the minimum weight from the 0, 0 to the bottom right corner, right? So to do that, we need to use a priority queue to help us do that. I'll explain a little bit later about this, how we are using this priority queue to make sure we get the correct answer here. And the starting point is of course is 0, 0, right? And then mm, and then for the Dijkstra problem, for the another variables we need for the Dijkstra is a dictionary for uh, for the minimum distance or minimum weight for each of the nodes. And so here I'm gonna call the either distance or cost. Okay, all right. And at the beginning, uh, at each positions, the cost from the start to the end will be the maximum, right? So here, since we have like how many positions we have, m times n, right? So that's why for each of the positions here, I and j, right? And that's the key basically. And the value of that will be the system maximum, right? Because at the beginning, since we will be since later on when we traverse the graph here, we'll be updating this cost dictionary when we have a smaller value, right? Since we're going to get a smaller value of this of each of the position, that's why we initialize it to be the biggest number so that we can always like get a smaller one, right? And for I in range M and sorry, for J in range N, right? So this is just like a shortcut to initialize this like cost dictionary, right? And one thing we need to notice here is the notice that the last one there's like this example here. Basically, if there's only one element in this 2D grid, right? What does it mean? It means that the start and end point are the same, which means we don't need to move at all, right? So that's why, because at this moment, at 0, 0 is also marked to be maximized, right? Maximum size. So that's why for 0, 0, right? It means that to get from 0, 0 to 0, 0, we don't need to do anything. Basically, the cost will be 0, right? And then, okay, so that's that. And cool, because the reason we need to use the cost here because we will be using the current cost values to be to decide if we want to update uh, because we need to use this one to keep the current smallest distance or different cost for each of the positions, and we'll be using this one to decide if we see a different path to this position, shall we consider that? That's why we need to use this like dictionary to store all those like the state for each of the position, right? And let me for the diagonal problem, the another use of that is the not only we need to get the minimum weight or maximum value, but sometimes it also asks you not only to find the value but also find the path, right? So to find the path from start to end, uh, even though we're not going to use these things in this problem, but I'm just listing that code here so that if you uh, are asked to find the path, you know how to do it. So the way we're doing the find the path is we are going to define a parent, right? A parent's dictionary for each node, all right? And we initialize it with 0, 0, right? So for the 0, 0, there's no parent, right? That's kind of obvious, right? And okay, so since we have everything we need here, let's get into the Dijkstra while loop here. Basically, while this priority queue is not empty, right? Then basically we do a current node, current distance, right? Or the weight or the cost. I I don't know which what I should call this thing. Cost. Yeah, let's do a cost. Cost. Okay, cost. Uh, I'll call it distance here. Ah, no, that's because on the in terms of a graph, it's a something like a distance, but in here it's like okay, fine. I'll call it cost here. Cost I j equals to heap q dot heap pop, right? Basically, what this one does is every time we're always trying to process the node that has the minimum cost at the moment, so that we can make sure we'll always be processing the minimum distance first to make sure we always approaching to the minimum cost for each node. Okay, and okay, and then let's do so once we have that, right? Okay, sorry, we also need to maintain like a scene stat, right? So that to make sure we won't be stuck in an infinite loop here. Basically, every time when we pop these things here, right, we do a scene dot add ing. It means that we already seen uh this uh this like positions, right? So that if in the future if we see this again, we don't have to process it again because we know we already seen the minimum value for this position, right? So that's that, and then for neighbor, right? In graph I and j, all right? Um, next I, sorry. Okay, sorry. So for the priority queue, the not only we need to push the state, the position, we also need to push the, like I said, the cost, right? And we need to put the cost at the first element because we want to get the minimum cost. So if you put this one in the first element, that's how this priority queue will be sorted based on the first element, based on the first element, right? So this one will be like the cost I and j, all right? So, but on the graph, since we're storing in a different way, maybe we should also storing it along with the along with this sequence, but it doesn't really matter, right? So this graph, it's fine. I'll just use keep it what it is as it is. So j, and this is gonna be the next cost, right? Next cost, and then and so we will with this thing we will be having a new cost here, right? What's the new cost? The new cost will be the current cost plus the next cost, right? And so now we need to do two checks here. So first is if the new I and new j not in the scene, right? And new cost is smaller than the the cost of this new I and new J, right? So what this thing tells us is the okay, first this is pretty, it's obvious, this new position must have not been seen before, and with this path, so the path is from this I, old ij to this new ij, and we're getting this new cost, right? By following this path to get the I and j. If this new path cost is smaller than our current cost for the new I and j, then we will be push it into the queue. If it's an even bigger one, then we don't even need to care about that, right? Because we know we we, we need the smaller one, right? Then priority queue heap queue dot heap push, right? Basically, we're gonna push the priority queue new cost, right? New cost, new I and new J, right? That's the queue. And we'll be doing two more things here. So first, since we have a new smaller cost for the new I and new J, we'll be updating our cost array dictionary here, right? New J with with the the new lower cost. And then we also need to update the parents, because since we have a better candidate here, we also need to update the path for that, right? Basically, the parent of I and j, new I and new j, now becomes to the I and j, right? Okay, so that's that. All right, and once this priority queue is finished, right, and then we can just simply do a return, right? So now we just need to return what? Return the last cost. Because now, remember, once we have finished processing everything, the cost dictionary will be storing the minimum cost for each of the position, right? And all we need is the last one, right? From this dictionary, which will be m minus 1 and n minus 1, right? So that should just work. Let's try to run it. Okay, so this one got accepted. Let's try to submit it. Cool, so passed. All right, so and a little bit of explanation about the Dijkstra problem. You guys can uh, maybe you guys can also find some other explanations on the internet, but I'll just do a quick proof of concept of Dijkstra here. Let's say there's like here, right? And then say there's a AD, okay? Let's see that the weight from A to D is 5, and then for A to B is 1, right? C is 2, also 1, okay? There's some others which we don't care, right? So E or whatever it is in the somewhere down the road, we don't care. So now let's take a look at D here, right? So there are two ways to get D to D. One is from A to D. The second one is from A, B, C, and D, right? And that's how we use this Dijkstra, sorry, the priority queue to make sure we will get the minimum cost to get to D. Why, right? Let's say from A, right? From A we have it has two edges. One is to the D, the other one is to the B, right? And we'll be pushing both A, B, pushing D and B into the priority queue, right? And then the next one got popped will be B because 1 is smaller than 5, right? And then uh, so we have a 1 and B, right? And then we have a 5 and D, right here. So one of B will be popped from the priority queue, and then there are like another different edges will be added to the priority queue, which will be C, right? So the C then we'll be having like a 3 to C, right? Because from 1 to 2 to get to C, the total distance is 3. Now we have 3 and C and 5D. Since we are using this priority queue to help us always keep the smallest distance at the very beginning, so the next one got popped will also be 3 and C, right? So 3 and C also got deleted, and now we have this what we have another D here, right? Which will be a 4 and D, right? 4 and D. So in this case, see, we already have like, so basically we have duplicated positions with different length here. Okay, so one more thing is the reason we can add this 4 and D into this priority queue here is because we have this two check here, right? Remember, so the first check is if I and J has not been seen before. That's the first one. Second one is that if the new cost is smaller than the current cost for the so in this case the new I and J is D, right? Because the first time we see when we add the first 5 into this queue here is we'll be updating this cost for D to 5. Now we see another way of getting to D is 4, and it's the new cost. And the cost is smaller than the previous one. That's why we can add this 4 to the priority queue, right? So now we have two two elements in the priority queue with the same coordinates but different cost, right? And then the first one will get popped here, right? So the 4 and D will get popped. And then we'll be using this 4 and D to calculate the the future, right? We'll be using the 4 and D to calculate the distance for E here, right? Because this one will get popped first, right? And then we'll be pushing the E based on this 4, right? To this priority queue. And someone may ask, right? Okay, and then what happened since we already have this 5 and D uh, in the in the in this priority queue? So the next time maybe 5 and D will also be gets popped, right? Correct. That's right. So let's assume once this 4 and D is finished, and the next smallest let's say we have a like 8E here, right? Okay, that's gonna be 4 and 4, right? So from 4 and 4, so now we have a 8E here. So then this one is gone, right? So the next time 5 and D will get popped, right, from here. And so 5D will get popped, and we can we can add an improvement here by even though the scene here is a set, right? Basically, we're trying to add this the D into the scene again, right? Which won't change anything, and then it will try to process these neighbors again. In this case, it's E here, right? and it sees that, okay, so is the E already has been processed, has been already seen before? No, right? Then it will, okay, but then it will try to check if the cost is the same, will is smaller than the current cost, right? In from D to E, the new cost we're getting is 9, right? Instead of 8, because at this moment the cost of E is we already updated from max size to 8, right? And so now the 9 is not smaller than the E, than the 8. That's why it won't be pushed here again. Okay? And the reason I'm saying that we can do a quick check here is we can save this for loop here and this check here by just do a simple check. If I and j is in scene, right? We simply continue, right? I mean, even though, but regardless adding this one or not, it won't affect our final result, because even though we are processing the same node again, but since we're always processing the first the smaller one first, and here we are adding a constraint by continue only if we have a smaller one. That's why even though we're processing the same node again, it will not affect our priority queue. But by adding this one, we can save the trip until to here, right? For the duplicate nodes. And another thing is that, let's say someone may ask, right? How can you prove this thing? Because this is just one example here, right? Since we have 5D, this one. How about what if like this is just it's a 7 here? Let's say there's sorry. What if this from 1 we change it to 6? Okay, and now this is another example, right? Basically, the 5 here becomes to the shortest path from A to D, right? And you know what? Maybe this is not a good example. Let's change this one from 6 to 4. All right. So let's say we have this updated graph here. Now the total path from A to D is 5, but from this side it's 7, right? Which means we should get 5. And how can our priority queue still make sure we're getting the correct answer here, right? Let's go over again. So at the beginning we have A and D. And we're getting 2 edges, right? And uh, okay, okay, I'm getting 2 edges here. Okay, so the first one is 5D and second one is 4B. Okay, and then the 4B will be popped, right? Since we're always popping the smallest distance, right, first. So the 4B is popped, and then a C will be added. But for C, the length will be 6, right? And 6 is greater than 5D. So when we push this C into the priority queue, it will be pushed. So it will be placed after 6, after 5, right? So now since we already because so that's how the priority queue can help us, like to make sure we always get the D first, right? Because at this moment, right, it doesn't really matter how many other nodes here, how many paths we can get from this C to D. Maybe there are 10 more ways to get from C to D, but we don't care, right? Because the cost to get to C is already greater than than the the 5 in this queue here, right? So that we don't care about all those the 5Ds, the 10 more ways to get from C to D, right? That's why this priority queue can help us. It always get the 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 quickest way to get to to this target here. That's why we're gonna be popping this 5 and D, right? And now the D has already been seen, and the minimum cost for the D becomes 5, right? So now once we pop the C here, right? So now the C here we have another D here, right? The D will be like 7. Uh, so now the 6C will get popped, right? And then from C we'll get like 7D, right? So now we have 7 and D, and 7 and D got popped, okay? And let's with this like small changes, the 7 and D will simply got skipped from here, okay? But assuming we don't have this, right? If we don't have the 7 and D, it will be going through this for loop again. Basically, we'll check the D here, the neighbors of D. But again, since we'll be we're trying to basically add this D to the neighbors of from D to the edges to E again, right? But the new cost will be smaller. Sorry, will be greater than the ones we already added to the E. Because once we pop the D here, right, we have a XE here, right? And this X will definitely be smaller than this 7D, right? And that's why it will be skipped from here, basically. It will be skipped from here. And so basically, regardless of adding this like if check here, the final result will be guaranteed to be correct. Uh, cool. I think that's about everything I can think of about this problem. Okay, let's do a real recap. Oh my God, this video has made a new record from my YouTube career here. So it had almost like 50 minutes. That's the by far the longest video I have ever recorded. All right, so let's do a real a quick recap here. First, first thing first, you have to first thing first. You cannot use DP, right? Like I said, it's DP. The current state cannot be depending on the future state. All right. First thing first is no DP in this problem. Second one is that how can we convert this problem into a graph problem, right? Because we're getting the minimum cost. That's either a BFS, a traditional BFS, or the BFS or the BFS with the weight on each edge, right? And in this case, it's the graph with weight. And then the second thing we have to figure out is how can we build a graph with weight on each edge, right? So on this problem is we have to utilize the, the the direction of each arrow, right? So which means following the same direction of the arrows, the weight on that edge is 0 because it means that there's no cost from that state moving to the next position. But if the direction is different as the arrows, then the cost is 1, right? And we have that weighted graph here. And then the next one is just a simple Dijkstra algorithm to calculate the shortest path, or in this case is the lowest cost from the beginning to the end. And these parents, I'm just adding these parents here just to help us to understand how can we, in case you're asked to find not only the minimum cost but also the path to get to the from 0 to this like final destination, right? And we can just simply use a for loop, right? For a while loop to start from the last element and then traverse back to the 0, 0, right? And then we just reverse and then in the end we just simply reverse the array that will give us the print as the the path, right? And cool, guys. I think that's pretty much everything I want to talk about this problem. Very cool problem. So it's combined like two things into its one hard problem. Thank you so much for watching the videos, guys, and I hope you guys enjoy my videos. I'll keep uploading some other videos in the future. And stay tuned and see you guys soon. Bye bye.